All right, so here is question number 4 and the solution for it. So it's a differential equation. And step A says, find the particular solution for that diff EQ with an initial condition at g at 0 equals 5. So when we solve the diff EQ, step 1, we need to have the ability to separate the variables. So we're going to multiply both sides by dx. Then we're going to divide by y minus 2. That way the y's are on one side and the x's are on the other side. So I have dy y minus 2 is equal to x squared plus 1 dx. All right, so step 1, and you get a point for that. Next step to do this is we're going to integrate both sides. So when you integrate, this is a fraction, and when I integrate the denominator, the numerator, the hook matches, so it's a logarithm. So ln y minus 2 is equal to. Now on the right side, I have x squared. So to integrate x squared, it's the anti-power rule. I'm going to add 1 to the exponent and divide. The integration of 1 is just x, and then we need the constant or the cookie at the end. Next, we're going to get y by itself. So to get y by itself, we are going to undo the logarithm. So to undo the logarithm, we're going to write it as an exponential. Recognize this last part, plus c, could be just written as e to the c. And then when you remove the bars, you can just simply redefine the constant. So that c2 is plus or minus e to the c. So now we just have a c2 in front, and then e to the exponent x cubed over 3 plus x. Next, we have a condition we need to plug in. So it says g at 0 equals 5. So that means the y coordinate is 5. That means the x coordinate is 0. And I think you can tell that if I plug in 0, you just have 0 in the exponent. E to the 0 is 1. So that means c2, or the constant's equal to 3. So putting it all together again, we're going to write down y equals. Now, right now we have y minus 2. So I'm going to write down 3e x cubed over 3 plus x, and then I'm just going to add 2 to the other side. All right, part B. This was the goal at the end here, to solve the diff EQ. It says, for the particular solution y equals g at x, found in part A, find the limit of that as x approaches negative infinity. So in other words, what's the limit as x approaches negative infinity of 3e to the exponent x cubed divided by 3 plus x plus 2. So as I put in a negative number, now if it was positive infinity, it would be simple because it's going to infinity. But as I put in negative numbers, what's going to happen here is that this number, e to like negative 1 billion, is going to be such a small number. And when you multiply it times 3, 3 times that is going to be very, very small. My daughter Juliana is here with me. So 3 times a really, 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 really small number. This whole part, as it goes to negative infinity, it's going to get closer and closer and closer to 0. And then the only part that's left over is the plus 2 part. So the limit as x approaches negative infinity of this is equal to 2. All right. Part C.
Why are you doing a lot of talking?
I know, right? Because I'm making a lesson video for my students in calculus. Isn't that fun?
Why?
Oh, because this way they can hear their teacher and do math with their teacher. So let y equals f at x be the particular solution to the given diff equation with this equation condition, f at 1 equals 3, and says let the value of the second derivative at the point 1, 3 is the graph y equals f at x concave up or concave down at the point 1, 3, and then give a reason for your answer. So I need to take the second derivative of what was given. Let's start there. So dy by dx equaled y minus 2 x squared plus 1. And I want to take the second derivative of that. Now, in order to take the second derivative of that, that's the d2y and dx2, I need to do the product rule. And then we're going to do this implicitly because x and y are mixed together. So what is the product rule? The first, y minus 2, times the derivative of the second. And the derivative of the second is 2x plus the second, x squared plus 1, times the derivative of the first. And that's just y prime. So the derivative of y is 1 and negative 2 is 0. That just leaves me with y prime. Now, in this situation, it gives you a value so that x is equal to 1 and y is equal to 3. This part here I need to think through a little bit. So y prime is dy by dx. So on the side, if I want to know what dy by dx is at that point, 1, 3, then into the derivative, I'm going to plug in 3 for y. I'm also going to plug in 1 for x because I need a value to plug in there. So I'm going to plug it in. 3 take away 2, that's 1. 1 squared plus 1, that's 2. So 1 times 2. What's the value of the derivative at 1, 3? And the answer is 2. So now I'm going to do a substitution. So if I'm plugging in at 1, 3, now that I took the derivative, where there's a y, I'm going to plug in 3. Where there's an x, I'm going to plug in 1. I'm going to continue that across. Now this part, what's the value of the derivative? That's what I did up here. So what does y prime equal at that point? And we figured it out, and the answer was 2. So now I'm going to just evaluate what I have. That's 1 times 2, and that's 2 plus times 2. So if I put that all together, I get the answer 6. So the first question is find the value of the second derivative at that point, and we did. So the answer is 6. The second part is the answer then, does that mean it's concave up or concave down? And because the answer was a positive answer, we need to write that down, d2 by d, this part here. So at the point 1, 3, it is greater than 0. Therefore, because it's greater than 0, it's positive 6. F at x is concave up. At the point 1, 3. All right, there's question number 4, dealing with the differential equation, separating variables, being able to work with it. Here we actually also had to do the product rule and did the second derivative and understand conceptually what's happening in terms of the calculus. All right, Mr. G Math, over and out.